All right. Today, what I wanted to do, in looking at the past paper questions, and you all can see those solutions on the Instagram page. I have them done up. We need to also know how to do the compound and multiple angle formulae, and to use those in solving trig identities, right? Compound and multiple angle formulae. Right, now they will give you these things at the start of in the formula sheet. So technically speaking, you don't have to memorize all of them, but like I told you guys, I prefer to know my formulae by heart as much as I can. And the more you practice with something and the more you write it out, is usually the easier it is to remember. I feel like this is bent. All right, anyhow. So let's start, shall we? So I'm just going to write them out, do a couple examples, print out that page for you guys, and then we're going to go through some questions on this, right? So let's start. So we have 6 of these formulae. We have sine of a plus b. All right, so this is equal to sine cos b, sorry, plus cos a sine b. Then we have the sign of a difference, which is basically the exact same thing as above, but with a minus inside of here, cos a sine b. All right. Now with the expansions for cosine, those have a slightly easier yet slightly, anyhow, let me just write it out. Trying to describe it sometimes just makes it sound more difficult than it actually is. So cos a cos b, but minus sine a sine b. All right, and then cos of a minus b is equal to cos a cos b plus sine a sine b. And the last one we have is, all right, last two, sorry, that's again. Okay, so tan a plus b and tan a minus b, these actually have fractions involved in them, but they're not terribly difficult. All right, so we have tan a plus tan b over 1 minus tan a tan b, and then tan of a minus b, sorry, that's equal to tan a minus tan b all over 1 plus tan a tan b. All right, then if you want something fun to try after the exams, you could try and derive these formulae. I did it 3 years ago. I have not been able to do it again since, and I refuse to look at the explanation in the book or anything on YouTube. I figured it out once, I can do it again. All right. Okay, so what we're going to use all these things for. All right, so let's take a look at a couple examples, right? So like I was saying, we're on page 333, right? We're just going to do a couple of the basic ones. I don't want to spend too long with this stuff because I want to get to the identity items, the expansions, all right? Okay, so we're going to take a quick look at, like I said, a couple of examples. All right, so we have example 2. All right, so example 2 gives us that sine A is equal to 4/5 and cos B is equal to 12/13. And without using tables or calculators, find the values of sine A plus B and cos A plus B. So we are required to find sine of A plus B and cos of A plus B. So we know from our expansion, we're going to need sine A, sine B, and cos A and cos B. Do we have all of that information down here? No, we don't. We have sine A and cos B, so we're missing sine B and we're missing cos A. Now, we use our old friend, the connection between sine and cos, which is sine squared A plus cos squared A is equal to 1 to be able to derive those things. All right, so from here, it would mean that to find cos A, what do we have? We have to do 1 minus what? Sine squared A, and then do a square root. All right, so if we square 4/5, what do we get? We get 16 over 25. If we use Yeah? No? All right. If we use our common denominators of 25, we get 25 minus 16 over 25, which gives us, what was 25 minus 16? 9. And the square root of 9 over 25, the square root of a fraction is simply the square root of the numerator over the square root of the denominator. Square root of 9 is 3, square root of 25 is 5. Now, with square roots, we know we could have a positive root and a negative root. What will guide us in our selection of the positive or negative root is the information about the angle A itself. What did the question tell us about angle A? Well, in option A and B are both acute angles. So we'll note here, A and B, sorry, capital A, capital B, my bad. Erase, please. Right, so A and B are both acute. So if they are both acute, in what quadrant will they lie? 0, 90, 180, 270. Where is acute? Acute angles lie between what and what? 0 and 90. So they'll lie here. And in that quadrant, which ratios are positive? All. So we will choose the positive value of the root here. All right. Similarly for we have cos B. Okay, so we have to find sine B. So sine squared B plus cos squared B is equal to 1. So to find sine B, what we have to do? We need 1 minus cos squared B and then find the square root of that. So that's the square root of, so what did it tell us cos B? That's 12/13, right? So that's 1 minus 144 over 169. So that'll give us 169 minus 144 all over 169, which is 25 over 169. And the square root of that will give us 5/13. You can use Pythagoras triples, yeah, if they're available, right? So Pythagorean triples are numbers, integers, that conform to Pythagoras theorem. So for example, 3, 4, and 5 is a Pythagorean triple, right? And if you look, it was 4/5, and the answer we got here was 3/5, right? But in the event you're not sure what the Pythagorean triple is, like for example, like with the 5 and the 13 and the 12, right? 5, 12, and 13 is a Pythagorean triple. But there may be some you're not too sure about. But most times, once they give you like a proper fraction, you should be able to like just square the denominator, square the numerator, and subtract. For example, if we took the 3/5, right? We could square the denominator, square the numerator, and subtract. That'll give us what? 25 minus 9, which is, sorry, it's supposed to be 4, right? It was 4/5. 4 squared. That gives us 16, which will then give us 9, right? So therefore, you find the square root of 9 to get 3. Similarly on this side now, if you had, what it was 12/13, alright, so you could do 13 squared minus 12 squared, so that's 160, whoops, not sure what that was, minus 144 equal to 25, and then you could square 25 and get 5, which will then give you 5/13. And this one here will give you 3/5. Right, so you have different ways you could do it. All right. Okay, and now all we have to do is plug those things inside of the expansion, right? So sine of A plus B. Where is he? Oh, wow, I was quite a way across on that side, right? So sine of A plus B will be equal to, like we said, sine A cos B plus cos A sine B. Right, so sine A, they gave us as 4/5. Cos B, they gave us as 12/13. So that's any question there, right? Cos A was 3/5, and sine B was 5/13. Whatever, so this is, don't cancel down stuff just yet. Work it out fully, because what's going to happen is you're going to have to end up adding those fractions. So we get 48 or the 65 plus 15 or the 65. And because we now have a common denominator, we could simply add the numerators. And so we go, all right? And similarly with cos of a plus b, that's equal to cos a cos b minus sin a sin b. Alright, so cos a was 3/5, cos b was 12/13, minus sin a was 4/5, sin b was 5/13. Once again, don't cancel down, leave it as it is. 3 by 12 is 36, so you have 36 over 65 minus 20 over 65. And 36 minus 20 will give us 16, so that's just a little less than a quarter. Alright. Okay, so what we're doing here is we are being given either sin A or cos A, or sin B and cos B, and have to find the other one. And then we have to use them to basically just facilitate the expansion, finding an exact value for those things. Okay, so in number 1, we have to simplify the following. So we have cos of a minus b minus cos of a plus b. Right, so yeah, 2017. Alright, so this cos a cos b plus sin a sin b minus cos a cos b minus sin a sin b. Now when you drop the brackets, what's going to happen is the cos a cos b is going to be negative, but the minus sin a sin b will become positive. So what that implies, therefore, is that the cos a cos b items will cancel out and the sin a sin b items will combine. So that will cancel with that, and we will get 2 sin a sin b. Got that? Yes? No? Maybe? Alright. Let's check part B now. Alright, so sine of a plus b minus sine of a minus b. Alright, so this is just to get you all familiar with the expansions by making you write it out. So sine of a cos of b plus cos of a sine of b minus sine a cos b minus cos a sine b. Sorry. Right, so when we drop the brackets, the sine a cos b will become negative. The minus cos a cos b will become positive. Cos a sine b, sorry. Which means that the sine a cos b items will cancel out. And the cos a sine b items will combine. So what's going to happen is you're going to get 2 cos a sine b. Yes, okay. We okay with that? Any questions, anybody, anything? No? Alright, cool. Alright, so that was number 1. Let's tackle number 3 one time. Alright, so we have cos of A is equal to 4/5, which therefore means that sine A is equal to 3/5. And we have cos of B is equal to 12/13, which means that therefore sine of B is equal to 5/13. Alright, lovely. So what do they want us to state? So A is sine of, whoops, A plus B. Alright, so that's going to give us sine A cos B plus cos A sine B. Alright, so what do we have from there? Cos A, sine A, that's 3/5. Cos B is 12/13 plus cos A is 4/5 by 5/13. Once again, I prefer not to cancel down. If you want to, that's fine. So we're going to end up with 36 over 65 plus 20 over 65, which gives us 56 over 65. Part B, cos of A minus B. So cos of A minus B is cos A cos B plus sin A sin B. Cos A, that's 4/5. Cos B is 12/13 plus sin A is 3/5 and sin B is 5/13. Right, 4 by 12 is 48 over 65 plus 15 over 65, which in this case gives us 63 over 65. So, alright, so far so good. Okay, alright, going again. And part C now. Oops. Okay, we have tan of A plus B. Right, so that'll give us tan A plus tan B over 1 minus tan A by tan B. So to find tan A, that's sine over cos, right? So sine A was 3/5, cos A was 4/5. So when you divide it, invert and multiply, we'll end up with 3/4, yes? Alright. Tan B, same thing. We have sine B over cos B. Alright, so sine B, that's 5/13. Divide, oops, that's not a divide sign. Divided by 12/13. Invert and multiply gives us 5/12. Yes? Alright. So tan A is 3/4. Tan B is 5/12. So we have 3/4 plus 5/12 all over 1 minus 3/4 multiplied by 5/12. Let's scroll down a little bit. Alright, 3/4 and 5/12 in the numerator. We'll use 12 as the common denominator. 4 into 12 goes 3 times. 3 by 3 will give us 9. 12 into 12, 1. 1 by 5 is 5. Your denominator is 1 minus. So 3 will cancel with 4, with 12 4 times. And we'll have 5/16. So we're going to have in the numerator 14 over 12. And the denominator will be 11 over 16. So that's going to give us 7 over 6 multiplied by 6 over 11. Sorry, 16 over 11. 2 could cancel with the 6 and the 16. So we get 56 over 33. These are the multiple angle expansions. You could call them double angle expansions, right? Because usually we use 2A or 2B, right? So first up we have sine of 2A. Now how do we get 2A? 2A is simply A plus A. So if we use our expansion for sine of A plus B, what will we get? We get sine of A by cos of A plus what? Cos of A by sine of A. Now sine A, cos A, and cos A, sine A is the same thing, right? And if you add something to itself, how many of that item do you have? You have 2. So this would be 2 by sine A cos A. Alright. Now I'm just going to show you something real quick here. You could even just take sine A and expand it, because you could simply call it, you could split A into 2 equal halves. You could split 1 into a half plus a half, right? So same thing here. You could have a half A plus a half, oops, a half A. Alright, which will give us same thing. So sine A over 2 cos A over 2 plus cos A over 2 sine A over 2. That's equal to 2 sine A over 2 cos A over 2. Alright. So anything that can be split into 2 equal halves, which is almost any number, even if it's an odd number, you just get, like if it was 3, you get 3 over 2, right? You can create an expansion for it. Okay, let's take a look at the cosine stuff now. So cos 2a, so that's equal to cos a by cos a. Sorry, let me follow my pattern from up above to show how I get that. So cos of 2a is cos of a plus a. Right? Obviously we can have cos of a minus a because a minus a would be 0, but cos of 0 is 1, right? But it wouldn't require an expansion to tell us that. Alright, so we need cos a by cos a minus sin a by sin a. Cos by cos will give us cos squared a. Sin by sin will give us sin squared a. Alright, now I can show you the same thing with the a over 2 or whatever the case is, but I want to show you something a little more involved here. And what is our first trig identity apart from sine over cos is tan? Our first identity is sine squared plus cos squared is equal to 1, right? So let's sine squared a plus cos squared a is equal to 1. So what that means is we could have a couple of offshoots here. Let's say we wanted to have cos squared only in the expansion here. How can we convert sine squared in terms of cos squared? Alright, 1 minus cos squared, not so? Now when we drop our brackets, what's going to happen there? The minus 1 will stick, but minus cos squared becomes plus cos squared a. And cos squared plus cos squared is 2 cos squared a. So we have 2 cos squared a minus 1. Similarly, with sine squared a, if we just wanted to have sine squared alone as the only trig function or trig ratio in the expansion, we'd have to convert cos squared into some expression with sine squared, which we know will be 1 minus sine squared a minus sine squared a. Sorry, that kind of looks a bit misleading. Right? So, sorry, this is option 1. I should say this therefore becomes 2 and 3. Alright, and 1 minus sine squared gives us what? 1 minus 2 sine squared a. Alright. And we have a couple of little things we could do addition onto that. So if cos of 2a is equal to 2 cos squared a minus 1, we could actually make cos squared the subject. Right? So I'm just showing you guys how you could play with this and manipulate it, right? Because these things really come into play not so much at the O level, to be honest, right? They really come in more to play at the A level, like if you go further to do like calculus with trigs, especially if you have to integrate trigonometrical functions. Sometimes you have to use your identities to boil them down to simpler forms to integrate, and then sometimes because trying to differentiate or integrate sine squared or cos squared could be a pain in the neck, to be honest. It's not that it's impossible, but it's just easier to integrate or differentiate where you have a coefficient of the angle as opposed to a power of the function. Alright? Okay, so here, for example, we could say, okay, so cos 2a, we could add 1 to that side and then divide by 2. And that'll give us cos squared a. Alright, similarly here, if you just bring it down, alright, so this expansion of cos 2a gave us 1 minus 2 sine squared a. So what we could do to make sine squared the subject, you could actually carry it across and bring this here. So 2 sine squared a, sorry, sine squared is equal to 1 minus cos 2a all over 2. Right? This stuff here honestly is just extra. I doubt you will have to use it, to be honest, but I just don't feel complete without showing people. It's almost like ASMR, I guess that's what I call it, right? It has to be satisfying. I don't feel satisfied as I show you all that stuff. It feels honestly incomplete. Alright, okay, and we have one more before we jump into a couple of examples, which is the tan. Alright, so tan of 2a, so once again, we could split 2a into a plus a and apply our compound angle formula, which is tan a plus itself, in this particular case tan a, over 1 minus tan A multiplied by tan A. So tan A plus tan A is 2 tan A, right? And tan A by itself is equal to tan squared A. Alright. So what we have there are what we call the multiple angle expansions. Alright. And yes, these have come in the papers, so they need to be at least relatively familiar with, a passing familiarity at the very least. Alright. So what we're going to do, we're just going to do a couple examples. Alright. You know, I honestly just want to go straight to the proofs, but I feel like if I do that, it might kind of upend the flow. So I'm going to take my time. All right. Before I go to the examples, anybody have any questions on these items? No? All right. Okay. Cool. All right. Yeah.
Actually, no, it doesn't make sense.
Okay. Cool. All right. So we're on page 341, actually. Sorry, 338. I'm going to do an example from there, then give you guys a couple of things to do. All right, let me just check this thing here. Print preview, see how many pages I'm on. Is that really critical? No, it's not. Oh, I'm on one page. Okay, cool. All right, let's get our line going. Okay. Example 9. I'm just going to do a couple of things with it, right? I'm not going to do very many things. So sine A is equal to 4/5. And we are told that A lies between 90 and 0, which means it's acute, right? So we know from here that cos A is equal to 3/5 because of Pythagorean triples and our previous work. And we also therefore know that tan A is equal to sine over cos will give us 4/3 in this case. All right, now what do they want us to find? We want sine 2A, cos 2A, tan 2A. Now, I've seen a cos 4A and a tan 4A. We'll bypass those for now. All right, may come back to them. All right, so sine of 2A is equal to, from above, 2 sine A cos A. All we have to do therefore is substitute our values inside. So 2 sine A by cos A. So 2 by 4 is 8, 8 by 3 is 24, and 5 by 5 is 25. Boom. Simple and straightforward, right? So that's part A. Part B is cos of 2A. That's equal to cos squared A minus sine squared A, right? So you could use that basic expansion there. So cos squared is 3/5 squared minus 4/5 squared. So sorry, no, cos squared is, yeah, cos squared is 3/5, all right. All right, so that's going to give us 9/25 minus 16/25, which is going to give us a minus 7/25. Right, so this implies that if you double the angle A is acute. If you double an acute angle, according to how big it is, it might go into the second quadrant, not so? And in the second quadrant, cos is negative. Right, so that is possible. That's not a non-solution. Let me just jump ahead to D. Right, tan 2A. Right, so this is 2 by tan A all over 1 minus tan squared A. Right, so let's do 2 multiplied by 4/3. Let's do a divide, right? Divided by 1 minus tan squared is what, boy? That's 4/3 squared. Alright, so that's going to give us 2 by 4/3 is 8/3. 4/3 squared is 16/9, right? 1 minus 16/9 is minus 7/9. So 8/3, right? Divide by minus 7/9. And we're going to invert and multiply. Multiply by minus 9/7. 3 will cancel with 9 minus 3 times. Right. So we're going to get minus 24/7. All right. Okay. All right. You guys ready? Well, let's take a look at that, all right? So cosine of A was equal to 5/13, and we have to calculate sine 2A, cos 2A, tan 2A. All right, so we know from our calculations and from earlier working that sine A is 12/13. Okay, so sine of 2a is equal to 2 by sine a cos a, which is equal to 2 multiplied by 12/13 by 5/13. 2 by 12 is 24, 24 by 5 is actually 120, and 13 by 13 is 169. Alright, part B, we have cos of 2a, right, which is simply cos squared a minus sine squared a. So cos squared a, that would be 5/13 squared. Sine squared is 12/13 squared. So that's 25 over 169 minus 144 over 169. That gives us a negative 119 over 169. Right? Does that make sense? They told us that A was acute, and if you double A, you might end up in the second quadrant. So 2A might be obtuse, and the cosine of an obtuse angle is negative. So that is possible. All right. Part C now is just simply tan 2a, right? Tan 2a. Okay, that's simply equal to 2 by tan a all over 1 minus tan squared a. Okay, all right, so we didn't work out tan a, so we can work that out up here, right? So tan a is equal to sine over cosine. Sorry, 1 second. Sine over cosine here will give us 12/5. So that will be equal to 2 multiplied by 12/5 all over 1 minus the square of 12/5. So that will give us 24 over, sorry, almost for 25, 24 over 5. Right, so this will give us 1 minus 144 over 25, which would be minus 119 over 25. Right, dividing fractions requires us to do what? Multiply by the inverse of the divisor. 5 will cancel with 25 5 times. 24 by 5 is actually 120 over 119. Okay, so once again, we are still in exercise 14.2. I'm going to try some of these proofs. All right, number 6. Okay, so 6 part A. We have sine theta plus cos theta squared is identical to 1 plus sine 2 theta. All right. So we know we could treatment it a little bit. We could say, okay, sine 2 theta is what? 2 sine theta cos theta, right? Okay, cool. So let's expand. We need perfect squares, right? So if we expand sine theta plus cos theta all squared, we get a squared plus 2a by b plus b squared. And we know that sine squared plus cos squared will give us what? 1, right? And we know from our work that 2 sine theta cos theta is equal to sine 2 theta, not so? Sorry, sine 2 theta, my bad. Alright, so first one wasn't so bad. Nice little easy introduction. Let's take a look at part B now. Part B has tan of theta identical to, oops, wow, that's not an n. I don't know what that is. That's not much better, but alright, we'll work with it. Sine 2 theta over 1 plus cos 2 theta. Alright, so which side here seems to have more meat? Left side or right side? Right side. I think so too. Alright, so let's take taking right hand side. Taking right hand side. Okay, so let's start with sine 2 theta over 1 plus cos 2 theta. So tan theta we know is sine over cos, right? So we're probably looking to kind of get it to boil down to that, right? But that denominator, anyhow, let's start. Sometimes you just have to take one step at a time and see where you're going. I see like you want to say something there. No? Okay, sorry. Alright, so we have 2 sine theta, cos theta. Now cos 2 theta, the basic expansion is cos squared theta minus sine squared theta, right? Oops. Don't understand. Go away. Right. Right. The numerator doesn't change. But that denominator, I suspect we could do a something like 1 minus sine squared. What's 1 minus sine squared? Cos squared, right? So your denominator now will become cos squared theta plus itself, which will give us what? 2 cos squared theta. 2 will cancel with 2. Cos will cancel with cos squared, giving us back cos. And guess what we're left with? Sine theta over cos theta, which is tan theta. Alright. Yeah, question? No? Okay. Okay, so they don't look that bad, right? But just like the rest from exercise 7.4 on Tuesday, there could be some challenging ones, but the objective of this is to get you all to think through it and to try things and see how it goes. You might try some things that end up in dead ends, you might try things that are completely wrong. The point is to try and see what works. And if something doesn't work, well, now you know that that does not work, and that's okay. Alright, so we're back on exercise 14.2, number 6. Alright. Let's see if writing, nope, writing bigger doesn't help at all. Alright, so we're looking at part C, right? Oh, okay, alright, I see we're going on with parts here already. Alright, so we have 1 minus cos theta over 1 plus cos theta. Alright, you all remember the trick that I showed you guys on Tuesday when you have stuff like that? Remember surds and you have to rationalize the denominator by turning it into the difference of 2 squares? You did that? Alright. So let's take this side. Okay, so we have 1 minus cos theta over 1 plus, cos theta. Now, we want it to get to be equal to tan squared of a half theta. So, remember I showed you guys some half angle formulae a little earlier? So, we want to get it to that. So, most likely we want to get like sine squared over cos squared of a half theta. Let's see. Alright, so let's try something. When things don't work out, like I said, that is just knowing what doesn't work. The challenge is figuring out what does. Alright, so we try to apply the difference of 2 squares, right? So let's try that. So we multiply by 1 minus cos theta over 1 minus cos theta. That would cause the denominator to turn into the difference of 2 squares, right? So the numerator would be 1 minus cos theta all squared. This would be 1 minus cos squared theta. What's 1 minus cos squared theta? Alright, cool. So let's go there. Sine squared. If we expand the numerator using perfect squares, what do we get? We get 1 minus 2 cos theta plus cos squared theta. Right. Okay, so I see what you're talking about. We're not sure what you have to do from here, right? Okay. What are our options? Well, if we factorize this again, we're just kind of going backwards, so that doesn't make any sense. If we change this back to that, once again, I don't think it makes any sense. So the only thing to do is to move forward. We could try to decompose the fraction. Now, remember as well what we're trying to end up as, right? Tan squared of a half theta. Now I'm wondering if there's an error in the question, but I'm seeing part D has something similar. Alright, okay, let's go. So clearly I've forgotten my old solutions to this, so this is actually a good thing. Alright, so it puts me in the same position you guys are in with not knowing what to do. So let's try something. Let's see if that idea has any merit, right? If we take 1 over sine squared theta minus 2 cos theta over sine squared theta plus cos squared theta over sine squared theta. Well, if we had to just use our inverted ratios, we'd be in luck because those things would work, right? We would simply get, what's that, cosec squared. Now, cos over sine squared, we can move the sign. I feel like I'm going in the wrong direction here. All right. Okay, so not sure. So if we got to that point and we're not sure what to do, we had to backtrack. We might have to backtrack all the way to the start, which is right here. So here we turn the denominator into the difference of two squares. What about if we did that to the numerator instead? What about if we multiply by 1 plus cos theta over 1 plus cos theta? Now I'm just spitballing here. What we were doing may very well have been the correct way to work it out. I just stopped short because it started to look like it ain't going anywhere I wanted to go. Alright? So let's try that instead. So let's try an alternative. So let's go back with our 1 minus cos theta over 1 plus cos theta. Let's multiply by 1 plus cos theta over 1 plus cos theta. So the numerator would boil down to this, 1 minus cos squared theta. Our denominator would be 1 plus cos theta all squared. Alright, what's 1 minus cos squared? Sine squared, right? So now our sine squared is in our numerator, which actually is not a bad thing. Because remember what we want to go to, right? Tan squared. Okay, cool. So if you want tan squared, sine squared over cos squared could work. But that's sine squared, but they want tan squared over half theta. If we expand that denominator, I wonder if expanding the denominator will just make it messier. Because if you want, oh wait, I think the correct thing was looking us in the face all the time. Suppose we didn't have to do difference of two squares at all. Suppose all we had to do was start off by changing all of these thetas to theta over 2. Isn't that where we want to go, to a theta over 2 answer? Alright. So just humor me for a second, right? Hold on, but you understand what I'm saying, right? We want to have in our answer not theta, but theta over 2, right? So
I thought you would have gotten that like
when
you divide
when it boils,
2 cos theta, so that's how you would have gotten.
no, but remember, if you divide 2 cos theta by 2, the 2 will cancel with the 2. The theta, if you want theta over 2, that has to be the initial angle you're dealing with. You can't just divide like sine of theta by 2 and get sine of half theta. That's not how that works. Alright? Alright, so we're stopping that there, and we're going back to 1 minus cos theta over 1 plus cos theta. Alright? So 1 minus cos of theta over 2 plus theta over 2 all over 1 plus cos of theta over 2 plus theta over 2. Yeah, sorry, handwriting, it's embarrassing me and all, boy. Okay. Alright, so what's our expansion for cos of 2 theta? Sine squared minus cos squared, right? So this gives us 1 minus sine squared. Sorry, not sine squared. It's cos squared minus sine squared. What am I talking about? Oh no, you know what I was doing? In my brain, already working ahead in the answer. So whatever my brain was on, that's what I wrote down. Right? So be careful with that, guys. That's something that could mess you up. Alright, so 1 plus, so cos squared theta over 2, sorry, I put them back in plus again, minus sine squared of theta over 2. Okay, when we drop the brackets in the numerator, the cos squared will become negative, agreed? And the sine squared will become, or the minus sine squared will become positive. Sorry, this is theta over 2, agreed? When we drop the brackets in the denominator, the cos squared theta over 2 will stay positive, and the negative sine squared theta over 2 will stay negative. Now, what's 1 minus cos squared? Sine squared. So sine squared theta over 2 plus sine squared theta over 2. All over. What's 1 minus sine squared? You'll see where we're going now. What's sine squared plus sine squared? Cos squared plus cos squared. Wow, I don't know what our number was, no? And what's sine squared divided by cos squared?
We just put theta over 2.
Right, because remember, when we first talked about the double angle formula, right? We took sine of 2a and split it into 2 equal halves, giving us, sorry, hold on one second. Sine of a plus a. And the implication here was that we could therefore take any angle and split it into 2 equal halves. So for example, if we just had, instead of sine 2a, let's say we had sine a, we could split a into 2 equal halves by dividing a by 2, right? So that will give us sine of a over 2 plus a over 2. As a half a plus a half a will give us back a whole a. Yeah? Alright, okay. Alright, let's try 6 part D, shall we? So, exercise 14.2, number 6, part D. Okay, so part D is that 1 minus cos theta all over sine theta is identical to tan of a half theta. So from a previous question, we saw that, okay, if we are going to the half theta, we probably want to split these thetas into half thetas one time. Okay, so we have 1 minus cos of theta over 2 plus theta over 2 all over sine of theta over 2 plus theta over 2. Okay, so 1 minus cos of 2 theta will give us, once again, cos squared minus sine squared of a half theta all over 2 by sine of a half theta cos of a half theta. Sorry, no, okay, right. Let's see now. So now we have 1 minus cos squared of a half theta plus sine squared of a half theta all over 2 sine of a half theta cos of a half theta. Alright, so what happens from here now? 1 minus cos squared is what? Aha, so we have sine squared of a half theta plus sine squared of a half theta all over 2 sine of a half theta cos of a half theta, and sine squared plus itself will give us 2 sine squared of a half theta all over 2 sine of a half theta cos of a half theta, and what could cancel there? 2 will cancel with 2, sine with sine squared, given sine in the numerator, so we have sine of theta over 2 all over cos of theta over 2, and sine over cos is tan. So let's take a look. So how far did you guys get? E, F, G, anybody? Anybody got to H? No? That's alright, that's okay. Okay, so let's take a look at that first one. So it looks like a distributive law thing that we have to do here, right? So we have alright, 2 cos theta, alright, plus 1 by 2 cos theta minus 1. That's identical to 2 cos of 2 theta plus 1. Okay, so that 2 cos of 2 theta, so remember cos of 2 theta has a few different appearances when you expand it. So what we're going to do, the most logical thing to do here is to expand, right? We probably won't be going to half theta things because that didn't factor into the answer. So let's try to keep it as simple as possible. So this is difference of 2 squares, is it not? So when you expand the difference of 2 squares, what do? We simply have to square the first term and minus the square of the second term, right? So 2 cos theta squared would be 4 by cos squared theta, and that's minus 1. Aha! Alright. So how does that help us? So remember, if we just take cos 2 theta, our initial expansion is cos squared minus sine squared, right? And then if you convert sine squared into cos squared, we end up with 2 cos squared theta minus 1, not so? Alright, now we have a cos squared theta, but we actually have 4 cos squared theta. 4 cos squared theta, right? Which is kind of double this, but the problem is it's missing that minus. I mean, we have a minus 1, but if you double this, wouldn't it be minus 2? That wasn't a trick question. Alright, okay, so check this, right? Imagine we doubled this side here, right? 2 cos squared theta minus 1. That will give us 4 cos squared theta minus 2. Agreed? Alright, so check this cheap trick. In order to make this minus 2, wouldn't we have to minus 1 from it? Right? But we can't just stick on a minus 1 just so. But you guys remember how the long process for completing the square? When you find half the coefficient of the x term and you square it, and then you do what? You add it and subtract it. So just follow me on this one, right? So if we minus 1 and plus 1, does that change anything? If you minus 1 and add 1 back, that kind of cancels off, right? But what it could facilitate is this. We could get our 4 cos squared minus 2. And 4 cos squared minus 2 is the same as that, not so? Right? So if you want to just show it as factorization, via factorization, sorry. And that would be 2 by cos of 2 theta plus 1. And that gives us what was requested. Right? So these ones, yes, these ones are a little more challenging. I'm not going to sugarcoat it. Alright? Alright, so we had 830. Anybody tried F? Yeah, alright. I'll just start off with a little more room. Oops. Why? Why is my letter formation so horrendous? Anyhow, F. Okay, so we have cos to the 4th theta minus sine to the 4th theta, identical to simply cos 2 theta. Well, look at that. What was the trick we learned in the last exercise on Tuesday? Cos to the 4th and sine to the 4th is still difference of 2 squares, right? So remember, if we consider a to the 4th minus b to the 4th, we could factorize this as what? A squared minus b squared, and then a squared plus b squared. Sorry. So we could do that, right? Alright, let's see what happens there. So here we will get cos squared theta minus sine squared theta by cos squared theta plus sine squared theta. What's cos squared theta plus sine squared theta? Not 1? And what's cos squared theta minus sine squared theta? That's cos 2 theta. So we just get cos 2 theta. So that's interesting. Cos to the 4th power minus sine to the 4th power is just going to give us back cos 2 theta. And you see our old friend cos squared plus sine squared came back into play, right? Alright. Anybody try G? Yeah? Okay, let's take a shot at G. Alright, so we have cot theta minus tan theta identical to 2 cot 2 theta. Now they try to pull one over on us here, because look at what this is here. This is 2 cot 2 theta. Do we have any expansion for cot of 2a or sec of 2a or cot? No, we don't. We have tan, right? But what's the connection between cot and tan? Cot is 1 over tan. So this is the same as 2 multiplied by 1 over tan 2 theta. Alright. So let's take a look. So we know cot theta is 1 over tan theta. And we have the minus tan theta from that. Okay? So common denominator would be tan theta. Yeah? Tan theta into itself goes 1 time by the numerator is 1. 1 into tan theta goes tan theta times. So we have tan squared theta. Behave yourself. Right. Now, I wanted to consider something for me. Sorry, not cot. I wanted to consider, our basic expansion of tan 2 theta. What was that? That was 2 tan theta over 1 minus tan squared, right? Sorry about the writing again. Now, this resembles this in that it is inverted, and the other thing is that it's missing the 2 down here, right? Okay, so how could we fix that, boy? Well, did I do it right here? Cot theta minus tan theta. Okay, 1 over tan minus tan. All right. So 1 minus tan squared. Okay, so let's consider double inversion, shall we? So 1 over 1 minus tan squared theta by tan theta over tan theta, sorry. So that will give us 1 over tan theta 1 minus tan squared. All right. Now, in order to connect these two things together, if we found half of that, we would get this, right? If you multiply this by a half, it would cancel the 2. So I'm not seeing how we get the 2 multiplied by that, but that's 1 over, let me have, was that 2 by tan theta? Sorry, tan 2 theta, my bad. Sorry, it's a half. Aha, that's it. A half that. Okay. I see it. Right. So check it. So that's 1 over tan 2 theta over 2. Which means that if you invert that, you get 2 over tan 2 theta, which is 2 by 1 over tan 2 theta, which is equal to 2 by cot 2 theta. And there you go. All right. Okay, this is an interesting one. It's very different. Yeah, even have surd forms and stuff inside of it. And that's equal to 1 plus sine 2 theta all over 2. Now, one of the tricks may be to observe pi over 4 minus theta. Pi over 4 is 45 degrees. 45 degrees minus theta. Well, unless theta is always going to be less than 45, the angle will be negative. And cos squared, well, that means you'll find cos of whatever the angle is and then square it. Okay. This side now, if we, let's say we play up with this side, right? So that's 1 plus 2 sine theta cos theta, and that's all over 2. And if we decompose the fraction, we'll get a half plus sine theta cos theta. Right, now how that comes back to this doesn't seem to be overly obvious. Cos squared. Okay, you know what? Let's take this piece here. But we're going to express it as cos of, hold on, cos squared. I want you just to consider this for a second, right? So consider that, remember, cos of 2 theta, one of the expansions was 2 cos squared theta minus 1, which meant that if we made cos squared the subject, we'd have to add 1 to this side and divide by 2. And that will give us, cos squared theta. So if we apply that here, we will get cos of 2 by the angle, which is pi over 4 minus theta, plus 1 all over 2. All right, that seems to be something along the lines of what might need to be done. All right, let's multiply that 2 inside the bracket, shall we? Using distributive law. Cos of pi over 2 minus 2 theta plus 1 all over 2. Let's expand that, shall we? So cos of a minus b will be cos of a cos of b plus sine of a sine of b, don't forget the plus 1 all over 2. Alright, now cos of pi over 2 is 90. Cos of 90 is actually 0. So before we go about expanding cos of 2 theta, when it just has to be reduced to 0, which, you know, negates any kind of expansion we probably need to do there. Sine of 90 is 1. So that expansion probably could be done. Plus 1. That's all over 2. Okay, so that's what I wanted, right? So that will give us 0, that will give us 1. So look at that. So you're left with sine of 2 theta plus 1 all over 2. Right, so like I said, I doubt they'd bring anything this complicated for you guys at this level, but you never know what they're going to bring, right? Sometimes they surprise even, sometimes they surprise you, right? Honestly, the stuff they've brought has not been overly difficult, but once again, that's only if you're well prepared enough, or well enough prepared, however you want to say it, right? Anyhow, this video is going on way long enough. Thanks for watching. I hope this has been helpful. If you have any questions, please feel free to let me know. I like to help. I like to make things easy for people, or at least help people to, I'm going to cut all this out anyway. I kind of lost track of what I'm saying. All right.